All right, so I want to work a couple more examples thinking of vectors in their horizontal and vertical components. So we have two vectors up here, A, which is -2, 4, and B, which is 3, -1. Remember that these give us both a magnitude and a direction, okay? So for example, I'm actually going to use a little marker board here, so that way you're not trying to look at my bad drawings. So if I want to sketch out A, okay, well, an easy way to start by sketching A is I can start at 0, 0, and then remember that these components give me direction. It says for my starting point, I'm going to horizontally go left 2. So there's 1, 2, and up 4. 1, 2, 3, 4. So here is our representation of A. Okay. Now I could also draw A anywhere else on the board. So I'd have a starting point. I'd go left 2 and up 1, 2, 3, 4. Okay. So there's another way I could represent A. Notice that those have the same magnitude and the same direction. Their position doesn't really matter. Okay? All right. So then if I want to represent B, okay, if I choose to represent B starting here, well, B tells me to go right 3 and down 1. So right 3, 1, 2, 3, and down 1. So there's a representation of B. I could also draw a representation of B anywhere else. I just take my starting point. I'd go left 3, 1, 2, 3, and down 1. Okay? So notice that it doesn't matter where I draw those, they look the same, right? They're the same magnitude, same length, and same direction. Okay? Now, if we want to work with these vectors, we're going to think about how we can scale them, add them, subtract them. That's what we're doing so far. Okay? So we know that when we add vectors, right, if I want to do A plus B, well, I can do that just by adding components, okay? So if I add components, right, another way to think about this is I went left 2 for A and right 3 for B. If I put those together, left 2 and then right 3, well, I'm going to be at an overall right 1. Okay? In other words, -2 plus 3 is 1. Vertically, I went up 4 and then down 1. That leaves me with a net of 3. Okay? Now, another way to think about vector addition, right, is if we're thinking about these geometrically, well, I'm doing, hold on, let me pause for. Okay, so then if we think about the geometric interpretation of addition, remember that we add tip to tail. So if I want to do A plus B, and I come back to our little board here, okay, I'm going to start with A, and I already have A drawn here, and then I'm going to add on B. So that means B is going to start where A ends, and remember B was right 3, 1, 2, 3, and down 1. So there's B. So here is our geometric interpretation of A plus B, and then the result of that, or the resultant, I can think of as going from the start of A to the end of B. And if we think about that vector, it has horizontal component 1 and vertical component 3. So it's the vector 3, 1, which is exactly what we got algebraically. Okay, so pretty straightforward. Now, one thing I want to talk about with the resultant is sort of a different way of seeing the resultant. Okay, so I'm actually going to do this on a little bit of grid paper because I think that's going to be easier for us to see. So we were talking about another way to see the result of A plus B. So in kind of our traditional way, right, I would take A, so here's my vector A, and I would add B to it, tip to tail. So there's A plus B, and then the resultant goes from the start of A to the tip of B. Okay, so this would be our A plus B. And notice that matches what we got when we did this algebraically. That vector A plus B goes over 1 and up 1, 2, 3, so its components are 1, 3. Okay, now what I want to do is turn this into a parallelogram by adding another copy of B down here and another copy of A on the other side. So I'm going to do that real quick. Okay, so I made another copy of B, so here's another copy of B, and here's another copy of A. And notice that all together, these make a parallelogram, or something whose opposite sides are equal in length and parallel. Now, what we use this to prove before is to show that B plus A, so notice that here I have B, and then I'm adding A onto the tip, is the same thing as A plus B. Or we use this to show that vector addition is commutative, okay, which is pretty useful. Now, what I want to do is make another, sorry, Piper's really excited about this. what I want to do is make another copy of this parallelogram to show sort of a different way we can show this result. So this is the result, A plus B or B plus A, okay? Okay, so notice that I've started to make a similar parallelogram, but instead of with the first parallelogram, sorry, I have a small helper today. With the first parallelogram, I started with A, and then I added on B. Sorry, she likes to be in the videos too. All right, Piper, say hi, and then we'll put you down, okay? Okay, sorry about that small but adorable interruption. So when I made this first parallelogram, I started with A, and then I added on B to create A plus B. Now, with this parallelogram, I just made A and B start at the same point. So there's A, and there's B, okay? But notice that this is actually going to make the exact same shape. Both of these are going to make the same shape. So what do I mean by that? Well, let me do a little bit of shading to see if I can clarify. Okay, notice that these two parallelograms are exactly the same, okay? They just kind of created them differently. But what does that mean? Well, it means that we can think of the resultant, that is the result of A plus B, kind of in terms of this picture. So tip to tail and then draw the result. Or I can think of it in terms of this second picture where I have A and B starting from the same point, and then the result is going to go from here to the other diagonal of this rectangle. So I'm going to draw that in. So there's the resultant. And notice that, again, those brown lines are exactly the same. So this is another way to represent A plus B, okay, as the vector that's formed when I create A and create, I can't do this backwards, when I create A and I create B, and then I draw in the diagonal of the resulting parallelogram. Both of these pictures are exactly the same. Both show the resultant, A plus B, but it turns out this picture is a little bit better sometimes for application problems. So if you're just thinking about vector addition, we can think about tip to tail and the result. But if we're thinking about things like forces and adding forces, this picture may be a little bit more useful. If I've got a point here and I've got a force going this direction, I've got a force going this direction, the resultant force, or the actual force, will be this vector right here, okay? All right, now let's think about subtraction. If I want to subtract a vector that's in its component forms, okay, I can think about something like A minus B. Remember, the easiest way to think of that is A plus a negative B. And then the real question is, how do we get a negative B? Well, if B is the vector 3, 1, that means from its starting point, it goes right, 1, 2, 3, and down 1, okay? So this is B. Negative B would go exactly the opposite way. So negative B would go something like this. Remember, a negative of a vector has the same magnitude, the same length, but goes in the opposite direction. So conceptually, that means our starting point is flipped, so we're starting down here, which means we have to go to the left, 1, 2, 3, and up 1. So negative B is going to look like negative 3, positive 1. In other words, it just flips the sign of all of our components. Then if we think about adding component-wise, right, A plus negative B is negative 2 minus 3, negative 2 or negative 2 plus negative 3, which is negative 5, and 4 plus 1, which is 5. So A minus B would be negative 5, 5, okay? The last thing we're going to do is we're going to talk about scalar multiplication. So remember, geometrically, scalar multiplication just means I'm taking a vector and I'm stretching or compressing it. So I'm changing the magnitude, the length of the vector, but I'm not changing the direction. So if I think about A, so if I have vector A, 1, 2, 1, 2, 3, 4, something like this, okay? Well, what if I want to do 1/2 of A? This would be a scalar multiple. A scalar is something that scales but doesn't change direction, okay? Well, 1/2 of A, right, would mean I would just take 1/2 of this vector. But that means that instead of going left 2, I'm going to go left 1, And instead of going up 4, I'm going to go up 2. In other words, I'm scaling each component by the scalar. So you can almost think of this as a distributive property. If I want 1/2 a, well, that looks like 1/2 of -2 times 4, but that looks like 1/2 times -2, which is -1, and 1/2 times 4, which is 2. Okay? So scalars, or scalar multiples, multiply through to components when we have things in horizontal and vertical component form. Okay? All right, I think I said that was the last thing alive, because I also want to talk briefly again about magnitude. So remember, magnitude is a fancy way for saying the length of a vector. Okay? So how do we find the length of something when we've got it in component form? Well, it turns out that's pretty straightforward, right? If we think about our vector, b, right? So b is the vector from its starting point, goes left, 1, man, I have said left every time, I'm sorry, right, 1, 2, 3, and down 1. So here is b. If I want to know the length of that, notice that this really can be thought of as a Pythagorean theorem problem, right? I can turn this into a right triangle. And I know for a right triangle, a squared plus b squared equals c squared, where c squared is the length of my vector. But how do I know what a and b are, right? How do I know length a and length b? Well, length a is just the horizontal component of my vector, in this case 3. Length b is just the vertical component of my vector, in this case -1. So to get c, well, c is going to be equal to the square root of a squared plus b squared. Okay? So in this case, c is going to be equal to the square root of 3 squared plus -1 squared. 3 squared is 9, -1 squared is 1, 9 plus 1 is the square root of 10. So the magnitude, or the length of this vector, is the square root of 10. And remember, to signify length, we use those things that look like, sorry, this is the length of vector b. We use these kind of absolute value bar things. Okay? So the magnitude of b would be 10. If we wanted to find the magnitude of a, the magnitude of vector a, again, is going to look like the square root of the horizontal component, -2 squared, plus the vertical component, 4 squared. -2 squared is 4. 4 squared is 16. 4 plus 16 is the square root of 20. I would need to simplify that. 20 is 4 times 5. So the square root of 20 is the square root of 4 times the square root of 5. The square root of 4 is 2. So the magnitude of a is 2 square root of 5. Okay? All right. So there's just kind of a review of how we can work with vectors when they're in their component form, horizontal and vertical component.